Rational expressions are one of the parent functions that we look at and study. There's a lot of interesting things that happen graphically with rational expressions, but before we look at the graphs, we want to kind of understand how we can operate with rational expressions and rational functions. So rational expressions are algebraic expressions that can be written as a fraction. And what's special about this fraction is that the numerator and the denominator are both polynomials. So all of those groups that we talked about and studied, constants, linears, quadratics, cubics, could be in the numerator and the denominator for a rational function. So it might look like something like 3 over x minus 2. We could have x plus 5 over x squared plus 25, so over a quadratic. But again, the big focus is that we should have some kind of polynomial in the denominator as we're working. Now, an important reminder is that denominators of a fraction cannot be 0. It's mathematically undefined to divide by 0. So we have to exclude or leave out numbers that we would plug in for x that would cause the denominator to be equal to 0. And so there might be 1 value, 2 values. Again, it's going to depend on the degree of that polynomial, because remember we talked about in the last unit that if it's a degree 2 polynomial, it would have 2 zeros. If it's a cubic, it's going to have 3 zeros. So we want to continue to kind of use that piece of information as we work here with finding the domain. So all of the x values that actually work for the function. So one way to find the excluded values of the denominator is to take your denominator, set it equal to 0, because again, we've got to figure out where it would be equal to 0. But now we're going to say, well, I actually want to leave these numbers out. So we could say not equal to. We can use the sign not equal to. So if we subtract 7 from both sides, in this case, b could not be equal to 7 because, negative 7, because negative 7 and positive 7 would cause that to be 0, which we can't do mathematically. So again, for the second one, we take the denominator, set it equal to 0, solve for the variable, and we say, oh, but that's the one that we actually have to leave out. So you can start with a not equal to sign, or you can do that, as your last step. If we look at this third example, we actually have a quadratic. And so just like we said before, this is actually going to have 2 excluded values. So we can try factoring. You could use quadratic formula. Any of those things that you have learned to solve quadratics. This one is actually going to be factorable. Because negative 4 times 3 would give us negative 12, and negative 4 plus 3 would give us the negative 1 for the middle term. And so now I have 2 values that I have to leave out from the domain. Now, one thing that does happen with rational functions is that we can simplify just the way that we simplify fractions. So remember, when we simplify fractions, that we eliminate any common factors in the numerator and denominator of the fraction. We can still talk about excluded values from the rational, and we should talk about excluded values, but we have to be careful because we have to make sure that our excluded values come from the original function. So when we simplify a rational function, we're getting one that I call it approximately equal. So if I were to graph the two functions together, they would look the same, but with some differences that might not be easily observed on the graph. And so to make sure that we're getting ready to kind of look at those scenarios, we do want to think about excluding values from our original function. So for example 2, remember that when you are simplifying fractions or things with exponents, we treat the numbers in the front like a fraction. So 7 would divide into both of those numbers. That would be a negative on the top, and we would have a 3, because 21 divided by 7 would leave us with 3. We have a squared over a to the 5th. So when we simplify this, this one's actually going to cancel out, and this would be, I would have 3 left. So we're just doing a little bit of division here. And then b to the 3rd divided by b to the 1st would be b squared. If you needed to write some of those things out, I mean, you can write that in expanded form and then cancel. Or you can remember your exponent rules, that you subtract the exponents to get your exponent when you divide. So from our original function, we had a b in the denominator, but in our simplified expression, we don't. But we would still have to make sure that we list that excluded value for our simplified expression. So if I graphed these, again, this is something I could graph, and I'd graph these two expressions would look the same. But we would have to say a cannot be equal to 0 and b cannot be equal to 0, because we're not adding or subtracting anything from that. We would just have to say we have to leave that out. So for the second example, 35 and 14, those are again are both divisible by 7. So we would have a 5 in the numerator, a 2 in the denominator. I don't have an x in the denominator, so none of that would cancel out. Y squared divided by y squared is going to cancel. And then we don't have a z in the numerator, so the z doesn't divide out either. But we have to look at what we had originally. We had a y in the denominator, and we have z in the denominator that we have to exclude. Most of the ones that we look at are going to look like this third example. They're just going to have a single variable. These are the ones that we can actually graph, and then we'll start to talk about some of the characteristics of the function. So we're going to factor the top. So things that multiply to give me 15, that when I add them I get 2. So that would be a 3 and a 5. A 5 would have to be the negative. And again, this is where we talked about if you're not comfortable factoring that this part may not go quite as quickly for you, but if you're pretty good with factoring, this should be relatively easy for you to see. We actually factored this one before. It's the same numbers, just with a different variable. And so we would then look to see if anything cancels. In this case, nothing cancels. I'd have to have the exact same terms inside parentheses to cancel the factors. So I can't simplify anymore, but then I would have to say that x cannot be equal to 4 because of this factor, and it could not be equal to 3 because of this factor. And again, to see that, you could take each of those, set them equal to 0, and solve. But the more you do this, the faster you'll start to recognize that it's really just the opposite sign. And so we can take that and quickly leave those, and actually need to say not equal to, leave those out of the domain. In example 3, we have a GCF in the top, so don't forget about GCF. Sometimes it's just as simple as factoring that out. The denominator will be a -5 and a -2. So we can cancel this entire term. We can't cancel things that are joined by addition and subtraction, so don't start to, if you're asked to simplify, like I couldn't look over here and just say, oh, I can cancel an x in the top and the bottom, and the -15 and the 10 would simplify. Those things are different terms of an entire expression, so we can't just take those and break them apart and work with those. When we write our simplified expression, we write it without the parts that we removed in the simplification. So again, these two expressions will look very much the same. However, this one would have 2 excluded values. We couldn't be equal to 2 or 5. So simplified expression along with our domain restrictions. And then for number 4, x squared minus 9 is a difference of squares, which factors x plus 3, x minus 3. In the denominator, things that multiply to give me 27, that when I add them I get 6, would be a 9 and a 3. The 9 would be the positive. So again, I can cancel, oh, not that one. Cancel the minus, not the plus. So my simplified expression would be x plus 3 over x plus 9. But I would have to leave out the variables, excuse me, the values of 3 and negative 9. So for simplifying rationals, again, the things I want to think about are factoring top and bottom, canceling any of the same factors, the things inside the whole group of the parentheses. We could also have numbers on the outside that can factor, just like we have the ones in the top, but we want to cancel anything that has in common top and bottom, and then we want to make sure that we leave anything out of the domain that would make our denominator equal to 0.